I just wanted to talk about a case study on Azadirachtin, on how these strategies were implemented to see multiple enhancements in productivities. Just to give you an introduction on why this molecule, Azadirachtin is a biopesticide. It's a high value phytochemical which is used as a biopesticide, as an alternative to chemical pesticides. I'll skip this. So, majorly commercially, Azadirachtin is being extracted from neem seeds, which is collected twice in a year. And during my introductory lectures, I mentioned that there is a lot of geographical and climatic variability. Although this is ubiquitous, but many of these species will not show you the same yield of Azadirachtin. And also, during the collection, there is contamination, because when the seeds are collected, they are ripe, and because of the large amount of sugar present in them, and they get infected by fungal pathogens. And these fungal pathogens also release, as a part of their metabolism, aflatoxin, which is a cancer-causing metabolite. So, this becomes a hindrance during extraction of Azadirachtin and a major issue during the usage and application of Azadirachtin. So it works as an anti-feedant. I'll just skip this. This may not be needed. This is just for your generic information. When this material will be available to you, if you want to know more about Azadirachtin, feel free to go through these slides. So what the group has done is, this is almost a 10 years work which has been consolidated. We collected literature papers and we could find what all has been done by the group on this particular molecule. The group also worked on cell suspension, and they also worked on development of hairy root cultures for production of these molecules. And a number of objectives were laid down. So when you are developing a bioprocess, the first objective, as I mentioned, was to develop your cell line or your culture system. So in one case, they were developing the cell suspension. In the other case, they were trying to induce hairy root from the explants. Then the second step would be, once you have the cell line in hand, you have selected a high yielding callus line or a high yielding root line. Then the point is to optimize the cultivation conditions to further improve the productivity, as I mentioned. So here's where in shake flask, you would try to implement all those productivity enhancement strategies before you take it to the reactor level, batch reactor level. So what did they do? They studied different strategies to see the impact on Azadirachtin titer levels from these cultures in cell suspension as well as in hairy root culture. Then what did they do? Once the process was optimized at the shake flask level, they took these culture systems to the batch reactor level. Now, before taking it to the reactor level, what is needed? There is always a scope for improvement. I will ask in the end, what are the gaps, and where, after listening to this module, what else you can propose which could have been done better. So then they went on to finding out the suitable reactor configuration for running a batch. Once they discovered a suitable reactor configuration to run the batch system, then the question came how to improve the batch productivity. So for that, they did kinetic modeling, process modeling, to design nutrient feeding strategies to overcome the limitations of batch. We were just discussing what are the limitations of batch. So they used mathematical modeling tools to overcome these limitations of the batch system to predict the nutrient feeding strategies. Now, once they get hold of an optimum nutrient feeding strategies, they implemented a fed batch process and a continuous process to see what further improvements can they achieve in Azadirachtin productivity. Then what did they do? So once they had done this in continuous cultivation, to further see if cell retention can improve Azadirachtin yields or productivities, bringing more cell-to-cell contact through cell retention, they also implemented perfusion-based reactor systems to see if that can be a good way to further improve Azadirachtin productivity. Now here, once all the cultivation up to the reactor systems were frozen, then they implemented the yield enhancement strategies, which they had also, like the elicitation and precursor addition strategies, the cell permeability enhancement strategies, at that optimized reactor level to see what best productivities can be achieved after integrating all these optimization strategies at the reactor level. I'll skip the protocols. Feel free to get into the details when you get the material. Now, so they collected large amount of seed varieties. So you remember I said first thing is to get hold of a high yielding cell line or callus line. Now, assuming that a higher yielding explant will lead to a higher yielding callus line, so first thing is to identify what can be the best explant. Neem is a ubiquitous, so it is present all across the country. So first thing is to find out where is the best explant line. So what did they do? They screened all the seeds collected from various parts of the country and they did an yield estimation analysis, and they could identify from these 23 to 26, if I'm right, varieties of seeds collected from various parts, that the Trivandrum variety was giving them the maximum azadirachtin yield. So they chose to pick up the Trivandrum seed variety for the in vitro cultures. Now, although they could have chosen this, the leaf or the plant parts directly as an explant, but imagine this is a group in North India sitting in Delhi, and then there is seed being collected from Trivandrum or the plant material then coming. So the viability is of importance. The plant material should remain viable. So what is the choice? You bring the seeds, quickly get them into an in vitro culture system and try to generate your in vitro plantlets. Another advantage of having in vitro plants would be that you can skip the process of surface sterilization. Because if you bring in the explants from outside, they will have surface contaminants. So first you'll have to sterilize and you'll have to come up with an optimized protocol for surface sterilization, at the same time ensuring that the cell viability is not lost in the explants. So it is easier said than done. It can take anywhere between 2 to 6 months. So you are saving that much time if you have in vitro plants. The third advantage is, once you have in vitro plantlets, they are more vulnerable to in vitro manipulations because they are young explants. So the younger the explants, they are more vulnerable to manipulations. So then what they did, they collected the Trivandrum seed variety, quickly got the in vitro plantlets as well. Now, every explant can also lead to different yielding callus lines. So they did a wide range of experiments where they used different tissues of the explants. They also used the seed directly to generate a callus. They could find that the callus, the highest yielding callus, was coming from the seed, which was sterilized and then used to directly give rise to callus. So once the screening and selection was done based on the growth index analysis and azadirachtin yield, they brought the callus into cell suspension. Can you see the cell suspension? It looks similar to how you see a microbial suspension. So this could happen because the callus line which they had chosen based on the growth index and azadirachtin yield must have been a friable callus line. So now what did they do? They started optimizing all those parameters like culture conditions, which included medium optimization and environmental parameters. Then they also did optimization of biotic and abiotic elicitors that could stimulate the enzyme activities in the biosynthetic pathway of azadirachtin. They also looked at precursor strategies which could be added based on the information which was available on the biosynthetic pathway of azadirachtin. They preferred to take the intermediates closer to azadirachtin for addition and see their impact as precursors. And they were also optimizing. This is all happening at the cell suspension level, at the shake flask level. So permeability enhancers impact, their impact on viability and on azadirachtin titers. First thing, what did they do? Now, before even you go for optimization, it's important to establish your growth kinetics. Now, growth kinetics is in terms of generally biomass profile with respect to time, the substrate profile with respect to time in the medium, and your product profile. So this is generally in simple terms your kinetics establishment. Now from this profile you can come to know whether it is growth associated, non-growth associated. You will come to know when is your highest azadirachtin titer coming, when is your highest content of azadirachtin coming in the batch. So why is all this of importance? Because that will also guide your harvest time of the batch. So therefore kinetics is important to draw. At this stage when you will draw the kinetics, you will have your base value known to you that this is my reference level of azadirachtin titer and productivity, because you know what should be the harvest time based on the highest titer in how many days are you achieving. So that should become your harvest time for the batch. Now this is your base productivity, this is your base yield. Now anything which you do for optimization should be able to get enhanced from this value. So that is why the importance of establishing the batch kinetics before you begin optimizations. So what did they find? They found that around 12th day they are getting maximum biomass, end of the log phase, and it seems to be a mixed growth associated product formation, wherein end of the log phase you are getting maximum titers and you are getting yield also, which is content. No, the other profile is for titer. So titer would guide your volumetric productivity. So where is your volumetric productivity? So your maximum titer is also on 12th day. So possibly 12th day becomes your harvest day for this control batch. So we'll keep calling this as control. Okay. Now what did they do? They, because there are well-known plant basal medium, they chose to first optimize. Now please note, unlike microbes, cryopreservation in plant cells is not a very well-known phenomena. Although DSMZ and many commercial entities do claim that they have cryopreserved plant cell lines, but if you see literature, it's not a very well-known phenomena in plant cells yet. So generally in tissue cultures, you will find working cell banks acting as master cell banks, which means the live cultures which you keep subculturing on solid medium, the callus lines, they also become your master cell bank. So care should be taken when you are maintaining these cultures. If a subculture period is of 15 days, you should not think that it does not matter if I subculture it after 16 days or 20 days or 25 days. It may impact. So the conditions, the media composition, the subculture period, the age of the culture, all that would guide the nature of the inoculum. So they did a plant basal media optimization and they could find that Murashige school medium was working best. So that became their maintenance medium for the maintenance of the master cell bank. Then they did also a basic check on what kind of carbon source would be good. Although sucrose is generally used, but they could find that anyways the glucose was giving them better results. They also did some single factor optimization studies to just find out in a range that where does the hill lie. Now before you start systematically optimizing the media composition, it may be good to see that in a wide range are you getting an inflection point or not. Especially when you are working with statistical optimizations, design of experiments, the range which you choose will guide the model which you get also heavily. If you choose a range in which there is no inflection point ranging, you will end up in a linear model, isn't it? Because it will be a monotonic, either increasing or decreasing plot. So what do you need to ensure? That the range of any parameter which you give in these designs should have a maxima, because you are looking for a maxima, so obviously a maxima in this case. So you need to see that the range which you choose for your parameters should not end up in a scenario where you are only able to see a rise continuously or a decrease. You must see a complete hill. Then only it's worth optimizing. Imagine if you will check only this point as a range where it was still continuously increasing, it has not yet reached to its maxima to beyond it decrease, then obviously the model which will show you the optimized value will be the end point, because you have not even realized what may happen after this. So therefore, sometimes it is of value to do these wide range single factors to identify the range which you should put in for statistical design of experiments. They did this, and interestingly, in this case, what they found was when you are doing these experiments, so they are trying to understand the requirements of the system. Generally, these media will have nitrogen in the form of nitrates or ammonium. They also tried to investigate the impact of these different inorganic sources of nitrogen. What they found that if you completely reduce nitrate to ammonia ratio to having only ammonium, it has significantly reduced the azadirachtin. And if you completely remove ammonium, it is increasing your azadirachtin. So which means that ideally you should not have any ammonium if you want azadirachtin to maximize. So then why should I do media optimization? Even though to begin with my basal media had ammonium, I'll be a fool to continue to have ammonia, isn't it? Ammonium chloride source. So now when I'll design of experiments, I will make a range 0. First thing, I'll not have an ammonium source, and the second thing, I'll try to replace ammonium nitrate kind of salts with only potassium nitrate, let's say, with only nitrate sources. And in the nitrate sources, I will try to identify what can be the best possible concentration. Then what did they do? Similarly, for all major salts, they wanted to ensure that the hill is lying in the range. If you are now, it is not necessary to do single factor experiments to identify this. How you can reduce this? You can reduce this from literature cues. You'll go back and see literature on similar species or in the same species, and you might be able to identify what should be the best range possible. Then you can skip this step. What did they do then? They picked up the major nutrients in the inoculum, and also they included inoculum size. So they picked up major components to optimize, to first screen. It was not an optimization experiment. It is to screen and rank what are those best nutrients and inoculum. Is it inoculum size? Is it a good parameter to optimize or not? So they did Plackett-Berman design here. The purpose was, even though it's a linear model, but the purpose was to identify and rank the most significantly impacting parameters on azadirachtin. What did they find? They ranked, and so what happens when in this polynomial, when you get the coefficient values, those coefficient associated with your parameters will also talk about the significance associated with that particular parameter. So based on that, you rank, and based on the sign, you come to know that in the given range, if you will keep increasing or if you will keep decreasing, whether it will positively impact or whether it will negatively impact the response. Based on this ranking for response surface for optimization now, they chose glucose, nitrate, phosphate and inoculum. Now, I was just mentioning, I'll just check if that is true here. See, the inoculum level is top ranked for growth, but if you see for azadirachtin, the top ranked is phosphate. Generally, phosphate won't come for growth. You will find inoculum, obviously, inoculum is a big impact. Then carbon, nitrogen, these things will show up. But for product, it may not be the case. So, as mentioned here, the top ranked seems to be the phosphate, then comes the carbon, then comes inoculum, and then comes the nitrogen. So therefore, it's sometimes good to have them as separate responses, because that will eventually also help you to design two-stage if you think so it is required. So based on this, what they could find, now getting a fully converging contour plot is the best case scenario. Why? Because that tells you that you had chosen the right design space, the right ranges for all your factors. If you are getting diverging plots, that is an indication that possibly the maxima is lying somewhere outside the design space, which is an indication that probably the design space which you have chosen was not right. Okay. Nonetheless, in the end, whatever is done has to improve the productivity. So what they could find based on this model simulation and optimized values of these parameters, when they did the experimental, they could achieve better azadirachtin yield. So let's see where they were earlier. So here the biomass concentration was 15 and azadirachtin was 2.9. What was the control value? If anybody remembers. Very good, not bad. So the biomass was just at 5.9 and azadirachtin was 9.3 mg per liter. So how much will it be? Approximately in milligrams per gram. 9.3 divided by 5.9, it will be somewhere around 1 point something, isn't it? Mg per gram. And where have they ended up in now after optimization? 3. Not bad. It has improved. The biomass has almost threefold improved, isn't it? And similarly, azadirachtin improvement. The next stage, what they did growth regulators, which we were talking about. So these growth regulators, when they were optimized, the response was azadirachtin titer now, so that they could club both biomass and azadirachtin content in one shot. So when they looked at, so what all matters here? The ratio of auxin to cytokinin and the concentration of both. Based on this, then the red highlighted one seems to be working best. 4:1 ratio of kinetin and BA, benzyladenine. Then optimization of culture conditions were done. See, I was telling you, it may not be visible to you directly, but if you will start looking at the viability check, you will observe that right from 125 RPM, if you start increasing to 250 RPM, we are still nowhere close to microbial suspensions now will be running at similar RPMs, 200, 250, isn't it? So now you see there is a continuous decline in the viability of the plant cells. So therefore, what kind of an RPM? 125 was chosen because it was given more than 95% of cell viability. They did the similar statistical design for pH and temperature, and they did. So in this case, the range chosen seems to be very good, and they could see. So this is a snapshot of how the improvement has happened. Unoptimized was here, and optimized has given them 3.1. So this is how they have finally improved with these culture conditions. Then they did elicitation. What did they do in elicitors? Following elicitors were studied. So they are all either signaling molecules or they are all biotic in origin, isn't it? So they have tested these signaling molecules, the top 3, and the later ones are all your biotic elicitors in different ranges. These are all single factor optimization studies. So salicylic acid seems to be giving the best results. Then what else is giving? Chitosan is also giving a biotic elicitor. So this is also giving you best result. 139. So now your titer has gone to 139. So elicitation, as I was mentioning, is one of the most successful strategies until date for without doing any genetic transformations if one has to improve secondary metabolite yield. See, 8.9 is your mg per gram azadirachtin. So it's a significantly improved value. Now what did they do? This is all single elicitor experiment. They thought that what if we do a synergistic effect testing of all these elicitors? So they chose to do a combined study using a central composite design to study the impact of combined addition of salicylic acid, chitosan and jasmonic acid based on the rank which they might have seen during the elicitor studies. What did they achieve? Azadirachtin yield C significantly has improved. So it has been an additive effect. So now azadirachtin yield has gone as high as 17 mg per gram. So that's the advantage. But can you see the dry cell weight, the biomass? It's 10 grams per liter, although we had reached 15 by then. So it seems to be, as expected, an inverse relationship. But what matters? Still, they would have chosen to go ahead with this. Why? No product. What matters more? Product, obviously. And what? Productivity matters. So even though the biomass has reduced less, but if the yield has gone way up, the product of both the entities might have ended up in better titers of azadirachtin than the control. Okay, I'll skip this. Optimum elicitor's value. So now they have ended up in 15.9 mg per gram after synergistic effect and contour additions and all. Okay. Now what else is to be optimized? I told you during the lectures that not only the type of elicitor, but the time of addition also matters. So they chose to do that study and adding it on 8th day of the cultivation. So 12th day was the harvest in batch. When they did this study, if they are adding on the 8th day before the harvest, it is resulting in best titers on the harvest day, which is 243 mg per liter. Significant improvement in terms of titers. So time of addition is also playing a role. Then they came to precursor addition. For precursor addition, what is important? To know the biosynthetic pathway. They investigated what all is involved. So the red highlighted ones which they chose the intermediates to add in the medium. Sometimes it may be also based on the availability of the standards, the molecules. So they added acetate, mevalonate, IPP, GPP, squalene. These things were added as precursors in this range, and they could find that mevalonic acid lactone was giving good results, IPP was giving good results, GPP at 1000 was giving good results, microgram per liter. And what was SL? Squalene was also giving good results. Okay. So now, what is giving the best result? The black highlighted one, which is your sodium acetate. Now, especially the group, although they saw that sodium acetate was giving the best result, the question came that is it being used as a precursor or is it ending up as an elicitor? See the biomass value. So then it has dipped. So now they wanted to know that what role is this sodium acetate playing. So let's say if a similar question comes to you, how would you identify that it is acting as an elicitor or as a precursor without doing many complex experiments?
Biomass is not showing, so it might be acting as an elicitor. Preventing the transmission, but limiting the metabolite thing.
Right. It may have some toxic role to play. Maybe it is changing the pH of the medium, such that which is inhibiting the growth. But ideally speaking, just to find out what was the basics of precursor, the utilization aspect, isn't it? So if you can do an analysis in the spent media to check whether what you added and on the day of harvest, it is the same or it has been used up, that is a fair indication to tell you whether it has been taken up as a precursor or not. Permeability enhancement was also checked. They chose to use these 3 organic solvents in these range, and they could find that N-hexadecane was giving them 13% release in the medium. So I told you it's very challenging and maybe very difficult also to achieve 100% release. It may not be possible. It's only possible when the cell lysis happens. So, but 13% release could be achieved at these conditions, because please remember, these will be toxic to the cells as well. So they have to be the percentage, the concentration of these organic solvents which you will use should also be optimized so that they don't compromise on the cell viability. So once all this was done in the shake flask, then they came to the reactor part. Now the first question is, what kind of reactor configuration should be chosen? So they did some stirred reactor checks with change in impellers, and they also chose to run pneumatically driven reactors where bubble column reactor was also investigated. They established the kinetics. What did they find? that in the stirred reactor configuration using a centric impeller, which gives a club of axial and radial flow, seems to be giving better kinetics, better growth rates. So what they could achieve was a biomass of 15 grams per liter and azadirachtin titers of 50 mg per liter in 10 days. So this is at reference value. So please note that they have not done it as a relay system. So that's also point of question. Now, plant cells grow slow. So you may not be able to optimize in a relay manner the process. Rather, you can do it in parallel and finally run an integrated study to see what multiplication effect or synergistic effect it may have. Because a relay system of optimization will take a long time. So in 10 days, so kinetics has improved. Now the harvest time is 10 days. So productivity has improved. With a centrifugal impeller, because centrifugal impeller seems to be giving better oxygen mass transfer coefficients and lesser mixing times. So when they did that analysis, they could achieve 18 grams per liter in 10 days. So it is 72 mg per liter titer of azadirachtin. Now, if you compare centrifugal impeller with centric impeller, they could see this result of better titers could be because of the fact that the biomass production rates have improved, the product production rate has improved. Why? Because the KLA seems to be better, significantly better, and the mixing time is almost the same, I would say, not significantly changed, but oxygen mass transfer coefficient has significantly improved. That could be the reason. So then they did, also they tried a bubble column reactor setup, but in 12 days was this. So finally, I think they chose to go ahead with centric impeller. Now, it is at this stage that you will again generate your kinetics. Why? Because reactor kinetics would be different from your shake flask kinetics, can be different. So therefore, it is recommended to draw your kinetics again. So based on this kinetics, then they now have the data of X, S and P with respect to time. They use this data to develop a mathematical model to explain how is the biomass production rate happening is dependent in terms of substrates and biomass concentration, how is the substrate utilization rate getting impacted, and how is the product formation rate getting impacted. I'll not get into the details of mathematical modeling, but it is here where you can, based on certain assumptions, every model has an assumption, but the key significant impact factors can be brought in the model to see the impact, to have the prediction power. So what they did, they wanted to use this model for designing nutrient feeding strategies later for fed batch. So they preferred to also take into account the substrate inhibitory effect, because when you run a fed batch, you try to feed in high concentrations of substrates at various flow rates such that you can maintain the concentration of substrate at any given time in the reactor less than the inhibitory value. So for that, this will come handy. So they developed a mathematical model. They did some experiments to get the inhibitory values and inhibitory kinetics so that they could incorporate in their biomass production rate equations. And based on certain assumptions, they came up with equations which can explain the biomass formation rate, equation which can explain the product formation rate, and equations which can describe the substrate utilization rate. So once they had done this, the next step is to use this, fit the model with the data which you have collected, and that fitting was done by using some mathematical tools. Generally, numerical techniques are used. These are iterative process starting with initial guess. Numerical methods are used. So then they came up, so any equation, mathematical equation I said will become a model if you'll assign definite values to the coefficients. So now they were able to assign definite values, and it is called a model when you can have some biological significance associated with those constants. Otherwise, anything can be modeled. Even my talking, my walking, based on whatever parameters I want to relate it with, it will fit in some polynomial. But that is not necessarily a model to adapt, extrapolate, because there has to be some physical significance associated with those model parameters. So like for example, here there is a maximum specific growth rate constant, there is your substrate affinity constant, monod saturation constant, which you say, then there is a maintenance coefficient, yield coefficient. So they all have their biological significance, which are constants in your model equations. What did they find based on this? This is just the simulation part, and to show that their model was fitting nicely to the data which they had provided. Now, once the model is ready, now is the time to use the model to do predictions. So what they did was, they used the same, because now the model parameters are kinetic constants of the culture, which do not change. Now these kinetic constants were used in the design equations for fed batch cultivation, which is an open system. The equations, this is nothing but material balance happening for substrate, product, and biomass. So they have done the material balance, they adopted the model parameters which they had devised from batch, and they came up with a fed batch model. Now what is extra in fed batch? What would you like to do? You would like to feed in the substrate. So what all can change? What can be the different permutation and combinations possible? The feed concentration you can play around with. The time of addition of the feed you can play around with. The manner in which you add the feed you can play around with. You can choose to have a constant feed rate. You can choose to have a linear feed rate, increasing feed rate. You can choose to have any exponential feed rate. Then for how long you are feeding is also a parameter. So you can imagine how many permutation and combinations can be made when you are designing nutrient feeding strategies. So then is the advantage of mathematical modeling, because you have predictive power in hand. So now what did they do? They simulated many strategies. In fact, we had done the similar thing for Viola cell suspension cultures. 29,000 strategies were simulated, and out of those 29,000 strategies which was simulated sitting on the computer, we picked up the optimum strategy for experimental validation. And you can imagine how much time will it go if you start doing experimentally and design nutrient feeding strategies to get to an optimum value. So how much time has been saved? So they played around with these 4 parameters in the fed batch, and based on the simulation, this was the design strategy which they experimentally implemented. What? You run the batch till 8th day. On 8th day till 12th day, you start feeding glucose at the rate of 0.05 liters per day. The phosphate feeding should be at 1 grams per liter. See, the feed concentration is also given. Again, at the same feed rate you should do, but here both the feeds have different initial concentration. They are separate feeds. From 13th to 14th day, stop the glucose feeding and start feeding nitrate of 35 grams per liter at the rate 0.05 liters per day, along with phosphate, which is now 500 grams per liter at the same flow rate. It's a very complicated strategy to even think and assume that this will give you better results. So now when they implemented, what did they get? 90 mg per liter Azadirachtin in 14 days with a biomass of 22 grams per liter dry cell weight, which is near to what they were achieving in shake flask. Now, the fed batch cultivation was done. This is the fed batch kinetics. How? Because the minute you will feed, you will see the spike happening. So this is just a kinetics to show. So how they are getting in 14 days. Similarly, they did the same thing with continuous cultivation. The model would change, and in this, they also brought in a cell retention device so as to run high cell density cultivation. This was a spin filter which they added, and they ran the continuous strategy, what is given on the slide. The model had predicted 139 grams per liter of dry cell weight, which means that much is the biomass. And in 26 days, you would achieve 130 milligrams per liter of Azadirachtin. what they could achieve practically, because why is it not always matching the model? It is based on the model, yes, certain assumptions not being taken in, but now becoming significant as the cultivation is happening. Like what I said, in our model, we didn't take into account the non-Newtonianness, neither they have. The hydrodynamic impact, which might be having a role here, which is worth considering if you want to make. So no model is the model. Every model is a model, and there is always a scope for improvement. But nonetheless, what matters? You should have in lesser time spent for optimization with reduced time, source, and energy, you have been able to achieve better results. So what did they choose? They chose to do finally process integration based on whatever optimization studies they had done. They added elicitors in that continuous reactor, and the maximum azadirachtin titers was 161 mg per liter, and in 10 days. So which means 11 mg per gram in 10 days was what they could achieve. Finally, they ran continuous cultivation with nutrients, elicitor, renewal, precursor addition, and permeabilization. So complete integration was done. This is how the integration was done. So cultivation was done in batch mode. Then from 8th day, they converted it into continuous cultivation with cell retention and elicitor feeding from 8th to 40th day. Continuous cultivation was continued. So cultivation was then continued in batch mode. Oh, okay, sorry, continuous cell retention. So now after 40 days, they chose to stop the exit and run it like a cell with the cell retention device simply as a batch. This could have been done because so as to bring in economics. Continuous, they might have seen a lot of substrate still remaining in the spent media. So they would have preferred, rather than harvesting on 40th day, they would have chosen to run it as a batch until, because now the cells anyways are no changing. What you want, if the cells can further take up whatever substrates it has and give you, if possible, better outcome. So they wanted to make full utilization of the spent media. So they continued it for 3 more days, finally terminating it or harvesting the biomass after 44th day. So finally, what have they achieved? 751 mg per liter of azadirachtin. So in a snapshot, if we see, this is how it goes. Batch with centric impeller, where do you stand? 5 mg per liter per day. Then with centrifugal, it is 7.2. Bubble column is an outlier where there is not much significant improvement from centrifugal. So fed batch, they did it with centric, easier to implement possibly. Some improvement there. Continuous has given them significant improvement up to 10. Then batch cultivation with elicitor addition is 16, and continuous cultivation with all the integrated study is giving them 17. So which is significant improvement in productivity. Now, this is one of the case studies by which if you systematically implement the productivity enhancement strategies, there is a good chance you will have multiple fold enhancement in product productivities. So if you compare their work with literature, I think they are from the seed kernel as the explant and suspension culture with precursor additions, they are relatively at a good stage. In terms of titers, they were the highest, which was 750. But in terms of yields and all, they are appreciably. But in the end, what matters is productivity, where I think they were the highest reported in literature. Okay, that's it. I think that ends. Yeah. So we'll be sending these. If you want to get in depth, there are papers published. You can get into the details.